Welcome to this video on solving problem number 101, Symmetric Tree. In this problem, we'll explore how to determine whether a binary tree is symmetric around its center. We'll break down the problem, discuss the recursive approach to solve it, and analyze its complexity. Let's get started. In this problem, we are tasked with determining whether a given binary tree is symmetric. A binary tree is considered symmetric if it is a mirror image of itself when viewed around its center. To break this down, for the tree to be symmetric, the value of the roots of its left and right subtrees must be equal. Additionally, the left subtree of the left tree must be a mirror of the right subtree of the right tree, and the right subtree of the left tree must be a mirror of the left subtree of the right tree. The input to the problem is the root node of a binary tree, and our task is to return a Boolean value, true if the tree is symmetric, and false if it is not. Now, let's look at a few examples to better understand the problem. In the first example, the binary tree has the root node with value 1, and its left and right subtrees are identical, with the left child having value 2 and the right child also having value 2. Going deeper, the left subtree of the left child has values 3 and 4, and the right subtree of the right child has values 4 and 3. This arrangement forms a perfect mirror image, so the output is true because the tree is symmetric. In the second example, the root node is again 1, and the left and right children are both 2. However, the left child of the left subtree is null, while the right child of the right subtree has a value of 3. This lack of symmetry between the left and right subtrees results in the tree being asymmetric. For the second example, the output is false because the tree fails to meet the mirror image condition. The left subtree, with its structure of 2 leading to a null node and then to 3, is not symmetric with the right subtree, which has the same structure but is oriented differently. In contrast, the third example shows a tree with just a single node having the value 1. Since there are no subtrees to compare, a single node tree is symmetric by definition. Thus, the output is true in this case. These examples demonstrate how different tree structures can lead to varying results depending on whether their subtrees maintain symmetry. Finally, let's consider the constraints and edge cases for this problem. The tree can have up to 10,000 nodes, and the values of these nodes range from -100 to 100. Edge cases include an empty tree, which is symmetric by definition, and a tree with only one node, which is also symmetric. If the left and right subtrees have different depths, the tree cannot be symmetric. Similarly, the presence of null nodes in one subtree but not in the other will break symmetry. These scenarios highlight the importance of carefully checking both the structure and the values of corresponding nodes in the left and right subtrees to determine whether the tree satisfies the symmetry condition. To determine if a tree is symmetric, we can leverage the idea that its left and right subtrees must be exact mirror images of each other. This insight forms the basis of the recursive approach. Here's how it works. First, the root nodes of the two subtrees must match in value. Then, the left subtree of the left child should mirror the right subtree of the right child, and vice versa. To implement this, we define a helper function isMirror that takes two nodes as input and recursively checks these conditions. The base cases are straightforward. If both nodes are none, they're symmetric. If only one is none, or their values differ, they're not. For all other cases, the function recursively verifies the symmetry of the left and right subtrees in mirrored order. This approach ensures we visit each node exactly once, making the time complexity O(n). The space complexity depends on the recursion stack, which is O(h), where h is the height of the tree. This makes the recursive approach both efficient and elegant for this problem. Another way to solve this problem is through an iterative approach using a queue. Instead of relying on recursion, we handle symmetry by comparing nodes in pairs iteratively. The process begins by pushing the left and right children of the root into a queue. Then, as long as the queue is not empty, we pop two nodes and compare them. If both nodes are none, we simply continue to the next pair. However, if only one of the nodes is none, or their values don't match, the tree is not symmetric, and we return false. When the nodes match, we enqueue their respective children in mirrored order, the left child of the first node with the right child of the second, and the right child of the first with the left child of the second. If we process all pairs without finding a mismatch, we conclude the tree is symmetric and return true. This iterative approach also has a time complexity of O(n), since each node is processed once. However, the space complexity is O(n) due to the queue size, which can grow with the breadth of the tree. A third approach, though less practical, is the brute force method of tree reconstruction. The idea here is to explicitly build a mirrored version of the original tree and then compare the two for equality. To do this, we first traverse the tree and construct its mirror. Once the mirrored tree is ready, we perform a comparison to check if the structure and values of the nodes match between the original tree and its mirror. While this approach gets the job done, it comes with significant downsides. The time complexity remains O(n), as both the traversal and the comparison require visiting every node. However, the space complexity is also O(n), not just for the recursion or iteration, but for storing the mirrored tree itself. This makes the approach memory-intensive and computationally redundant. Because of these inefficiencies, this method is rarely used in practice for solving symmetry-related problems. Among these approaches, the recursive solution stands out as the most natural and efficient choice for this problem. It directly mirrors the problem statement, using recursion to compare subtrees in a straightforward and intuitive manner. The code is concise, easy to read, and has a space complexity of O(h), which is better than the O(n) space required by the iterative queue-based method for balanced trees. However, it's worth noting that recursion does carry the risk of stack overflow in cases of very deep trees. When comparing the recursive approach to the brute force method, the advantages are clear. Avoiding the unnecessary overhead of reconstructing and comparing a mirrored tree makes the recursive solution far more practical. Ultimately, the key insight here is that symmetry boils down to comparing mirrored subtrees. For most cases, recursion is the optimal and most elegant way to capture this logic. That said, iterative methods remain a viable alternative for scenarios where stack depth is a concern. To determine if a binary tree is symmetric, we need to understand what symmetry means in the context of trees. A binary tree is symmetric if the left and right subtrees are perfect mirror images of each other. This symmetry requires three conditions. First, the root nodes of the two subtrees being compared must have the same value. Second, the left child of the first subtree must match the right child of the second subtree. Third, the right child of the first subtree must match the left child of the second subtree. To implement this, we can use a recursive approach. We'll define a helper function called isMirror that takes two nodes as input and checks if the subtrees rooted at these nodes are mirrors. The base cases for this function are straightforward. If both nodes are null, the subtrees are symmetric and we return true. If only one of the nodes is null, the subtrees are not symmetric and we return false. Beyond the base cases, we check that the current nodes have the same value and that their children satisfy the symmetry conditions through recursive calls. Specifically, the left child of the first node must be a mirror of the right child of the second node, and the right child of the first node must be a mirror of the left child of the second node. Building on this, we can now extend the symmetry check to the entire tree. The tree is symmetric if its left and right subtrees are mirrors of each other. To initiate the process, we call our isMirror function with the root's left and right children as inputs. Next, we handle some important edge cases. If the tree is empty, meaning the root is null, we return true since an empty tree is symmetric by definition. A tree with just one node is also symmetric because there are no subtrees to compare. It's crucial to ensure that our algorithm can handle imbalanced trees, where one side of the tree might be deeper than the other. There are three key insights to note here. First, the problem has a recursive structure. Symmetry at the root level depends on symmetry at smaller subproblems, making recursion an ideal approach. Second, instead of comparing nodes directly across the same side of the tree, we compare opposite nodes, such as the left child of one subtree with the right child of the other. Finally, by checking the base cases early, we can terminate the recursion as soon as we detect any asymmetry, saving computational effort. From a data structure perspective, the tree nodes can be represented as objects with attributes for their value and left and right children. Additionally, the recursive call stack is used to track the state of the nodes being compared, with its depth limited by the height of the tree. The algorithm revolves around three primary operations. First, we perform a node comparison by checking if the values of the current nodes are equal using t1.val equals t2.val. This ensures symmetry at the current level. Second, we make recursive calls with the left child of one node and the right child of the other, as well as the right child of one node and the left child of the other. These recursive calls enforce symmetry in the subtrees. Third, we handle base case checks. If either node is null or their values don't match, we return early to prevent unnecessary recursion. When analyzing the complexity of this algorithm, the time complexity is O(n), where n is the number of nodes in the tree. This is because each node is visited exactly once during the traversal. The space complexity is O(h), where h is the height of the tree. This accounts for the recursive call stack, which grows proportionally to the depth of the tree. Let's consider an example where the tree is perfectly symmetric. We start with the root node and compare the left and right subtrees. As we proceed recursively, we verify that the corresponding nodes at each level satisfy the symmetry conditions, confirming that the tree is symmetric. In the first example, we have a tree where the root node has 2 children with the value 2. At the next level, the left subtree has children 3 and 4, while the right subtree mirrors this with children 4 and 3. We begin by comparing the root's left and right children, which both have the value 2. Then, we compare the left child of the left subtree, which is 3, with the right child of the right subtree, also 3. Similarly, we compare the right child of the left subtree, which is 4, with the left child of the right subtree, also 4. Since all these comparisons succeed, we conclude that the tree is symmetric. In the second example, the tree is structurally different. The root node still has 2 children with the value 2, but this time the left subtree has a right child with the value 3, and the right subtree also has a right child with the value 3. When we compare the root's left and right children, they are equal. However, when we go deeper, we compare the left child of the left subtree, which is null, with the right child of the right subtree, which is 3. This mismatch immediately breaks symmetry, and we return false. This demonstrates how the algorithm efficiently detects asymmetry as soon as it occurs. This Python implementation solves the LeetCode problem symmetric tree by determining whether a binary tree is symmetric around its center. The solution uses recursion to check if the tree's left and right subtrees are mirror images of each other. We start by defining a helper class tree node, which represents nodes of the binary tree. Each node has a value, val, and pointers to its left and right children, left and right. The solution class contains the main function isSymmetric. The isSymmetric method first checks if the root node is none. If the tree is empty, it is symmetric by definition, so the function immediately returns true. Next, we define a recursive helper function isMirror to compare 2 subtrees, T1 and T2. The logic of isMirror is as follows. 1. If both subtrees are none, they are symmetric, so return true. 2. If only one of the subtrees is none, they are not symmetric, so return false. 3. Otherwise, compare the values of the root nodes of the 2 subtrees. Additionally, check recursively whether the left subtree of T1 is symmetric with the right subtree of T2, and the right subtree of T1 is symmetric with the left subtree of T2. The isSymmetric function finally calls isMirror with the left and right children of the root node to check for symmetry. This ensures that the entire tree is evaluated for symmetry. This solution has a time complexity of O(n), where n is the number of nodes in the tree, as each node is visited once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Here, we begin by defining the basic structure of a binary tree node using the treenode class. Each node contains an integer value, as well as pointers to its left and right child nodes. We've provided 3 constructors for flexibility, one with no arguments, one that initializes only the node's value, and one that initializes the value along with its left and right children. Below that, we define the solution class, which houses our logic for checking if a tree is symmetric. Within this class, the isSymmetric method is the entry point. It first checks if the root is null, as an empty tree is symmetric by definition, and immediately returns true in that case. If the tree isn't empty, we call the helper method isMirror, passing in the left and right children of the root node to evaluate their symmetry. The isMirror method is designed to recursively check if 2 subtrees are mirror images of each other. It begins by handling the base cases. If both nodes are null, they're symmetric and we return true. If one node is null while the other isn't, the subtrees aren't symmetric, so we return false. For all other cases, we compare the values of the 2 nodes. If their values match, we proceed to recursively check their children. Specifically, we confirm that the left child of the first node mirrors the right child of the second node, and vice versa. This ensures that symmetry is maintained at every level of the tree. The method returns the result of these recursive checks, ultimately determining whether the entire tree is symmetric. To solve the problem of determining if a tree is symmetric, we'll start with this first example. The input tree has a root node with the value 1, and its left and right subtrees are mirror images of each other. The isSymmetric function is first called with the root node. Since the root is not null, we then call the helper function isMirror with the left and right children of the root, both having the value 2. Inside isMirror, we check that the values of these nodes are equal, which they are. Next, we recursively compare their respective left and right subtrees. We first call isMirror on the left child of the first 2, which has a value of 3, and the right child of the second 2, which also has a value of 3. Both values match, and since these nodes have no children, this recursive call returns true. Similarly, we call isMirror on the right child of the first 2, which has a value of 4, and the left child of the second 2, which also has a value of 4. Again, both values match, and since these nodes have no children, this call also returns true. With both recursive calls confirming symmetry at this level, the earlier isMirror call also concludes with true. Now, with all symmetry checks at the subtree level confirmed to be true, the isSymmetric function ultimately returns true for this example, indicating that the tree is symmetric. Moving on to the second example, the input tree has a root node with the value 1, and both its left and right children have the value 2. However, this time the subtrees are not mirror images. The isSymmetric function is called with the root node, and as before, the isMirror function is invoked with the left and right children of the root. Both nodes have the value 2, so we proceed to recursively check their subtrees. Here, isMirror is called with the left child of the first 2, which is null, and the right child of the second 2, which has a value of 3. Since one of these nodes is null while the other is not, this recursive call immediately returns false, indicating that the symmetry is broken. As a result of this false outcome, the overall isMirror check for the left and right subtrees also returns false. Consequently, the isSymmetric function determines that the tree is not symmetric and returns false for this example. Finally, let's examine the third example, which is a tree with only a single node. Here, the isSymmetric function is called with the root node, which has the value 1. Since the root is not null, the isMirror function is invoked with its left and right children. Both children are null, so isMirror immediately returns true because a tree with no children is inherently symmetric. Therefore, the isSymmetric function concludes that this tree is symmetric and returns true as the result. When evaluating the time complexity of this problem, we see that it is directly related to the number of nodes in the binary tree, denoted as n. The isSymmetric function works by invoking the helper function isMirror, which recursively compares the left and right subtrees of the tree. In each invocation of isMirror, we perform a constant amount of work, such as comparing values and making recursive function calls. Because we need to examine every node in the tree to determine whether it is symmetric, the algorithm visits each node exactly once in the worst-case scenario. As a result, the total time complexity scales linearly with the number of nodes, giving us a time complexity of O(n). Now, let's consider the space complexity, which is determined by the memory used for the recursion stack. In the worst-case scenario, where the tree is completely skewed, meaning all nodes are aligned in a single branch, the recursion stack will store a call for every node along the height of the tree. In this case, the height of the tree is equal to the total number of nodes, n, resulting in a space complexity of O(n). On the other hand, if the tree is perfectly balanced, the height of the tree is proportional to the logarithm of the number of nodes, or O log n. This means that the recursion depth is limited to the height of the tree, and the space complexity becomes O log n. To summarize, the space complexity is O(h), where h represents the height of the tree. Depending on the tree's structure, this can range from O log n in the best case to O(n) in the worst case. Additionally, in the best case scenario where the tree is empty or contains only a single node, the function exits early with a time complexity of O(1). For a balanced tree, the time complexity remains O(n), and the space complexity is O log n. However, for a completely skewed tree, both the time and space complexities are O(n). To put this into perspective, let's compare the recursive solution to a brute force approach. A brute force method would involve traversing the entire tree to create a mirrored copy of it, and then comparing the original tree with the mirrored one node by node. This would result in a time complexity of O(n) for constructing the mirror, an additional O(n) for the comparison, and an extra space complexity of O(n) to store the mirrored tree. In contrast, the recursive approach avoids creating a mirrored copy and directly compares nodes, making it significantly more space efficient. From a mathematical standpoint, the recursion follows a divide and conquer strategy, where each node calls its mirror on its left and right subtrees. This ensures that every node is visited exactly once, which results in a linear time complexity of O(n). The depth of the recursion corresponds to the height of the tree, which determines the space complexity as O(h). In conclusion, the recursive solution is optimal for this problem, achieving a time complexity of O(n) and a space complexity of O(h), where h is the height of the tree. When working with symmetric trees, there are a few common mistakes to watch out for. One frequent misunderstanding is confusing symmetry with equality. Symmetry doesn't mean the left and right subtrees are identical, it means they are mirror images of each other. For instance, if the left subtree is 2, 3, and the right subtree is also 2, 3, the tree is not symmetric, because the structure doesn't mirror. Additionally, ignoring null nodes during comparisons can lead to incorrect conclusions. If one side has a null node while the other does not, the symmetry is broken. For example, 1, 2, null is not symmetric because the null node on one side has no counterpart. Another common mistake is setting up an incorrect base case in recursion. If you return true prematurely or fail to handle leaf nodes correctly, the solution might miss critical symmetry checks, especially in edge cases. Always ensure the base case fully validates symmetry throughout the tree before terminating the recursion. Inefficient traversal is another area where mistakes occur. Redundant calculations or visiting the same nodes multiple times can increase time complexity unnecessarily. A well-optimized solution should visit each node only once. Another pitfall is neglecting edge cases. You need to explicitly test scenarios like single-node trees, empty trees, or trees with only one child. These special cases can easily break your solution if they're not accounted for. Now, let's look at some insights for interviews. At its core, solving the symmetric tree problem boils down to comparing left and right subtrees recursively. This can be accomplished using recursion or an iterative approach with a queue for breadth-first traversal. Recognizing this pattern is valuable because it applies to other tree problems, such as checking if two trees are identical, determining tree height, or checking balance. While recursion is often the most straightforward approach, using a queue can be more space efficient, especially for large trees. When solving this in an interview, clarify edge cases with the interviewer, ask if empty trees or single-node trees need to be explicitly handled. This problem connects to several related problems that can deepen your understanding of trees. For instance, problem 100, same tree, involves checking whether two trees are identical. Problem 226, invert binary tree, requires reversing left and right subtrees, which is conceptually linked to symmetry. Problem 104, maximum depth of binary tree, focuses on recursive traversal, a technique you'll also use here. Now, let's discuss alternative approaches to solving the symmetric tree problem. The recursive approach is a natural fit, it involves comparing the left and right subtrees recursively. This is simple and intuitive but may lead to a stack overflow if the tree is very deep. An iterative approach using a queue avoids recursion limits and allows breadth-first traversal by storing pairs of nodes for comparison. However, managing the queue requires careful implementation. Alternatively, you could use an iterative approach with a stack for depth-first traversal. While this method is similar to the queue approach, it may consume more memory for deep trees. Each approach has its trade-offs, so choose based on the problem's constraints and your familiarity with the techniques. To wrap things up, we learned how to determine if a binary tree is symmetric using a recursive approach. By comparing left and right subtrees as mirror images, we achieved an efficient solution with O(n) time complexity. Remember, recursion is a powerful tool for tree problems. Thank you for watching, and don't forget to like and subscribe for more problem-solving content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!